This lesson is part 2 of section 10.1. We're going to continue to solve right triangle application problems today. We will also be able to express lengths and areas using trigonometric functions. Alright, we'll begin with this right triangle application question. Now this is definitely going to be a step up in terms of difficulty from the questions that we looked at in the previous lesson. So here we go. Alright, the angle of elevation to the top of a building at point A is 50 degrees. At point B, which is 100 feet further away from the building than point A, the angle of elevation to the top of the building is 42 degrees. Find the height of the building in feet. So the main idea here is to make sure that you're drawing an accurate picture. You've got some vocab terms here like angle of elevation, which we know from our previous lesson. That's the angle that's formed from the ground up. Now they also mentioned two distinct points here, point A and point B. Alright, so when we draw this in, we definitely have a building, so that's going to represent that vertical line here. So here's a building, little offices. How beautiful. Okay, now the points that they're talking about are on the ground because you're looking up to the building, up to the top of the building here. So point A and point B are definitely on the ground, and if I draw these in, I need to make sure that I label these correctly. There are two distinct points. One is farther away from the building than the other. So it says that point B is 100 feet further away from the building than point A. So I definitely want to make point B here, and I'm going to label this as 100 feet, which makes this point A. Now the angle of elevation looking from point A is 50 degrees. So here is 50 degrees. And then here it says that the angle of elevation from point B is 42 degrees. Now our goal is to find the height of the building. So I'm going to label this segment here X. That's representing the height of the building. Now obviously we are dealing with two right triangles here. They are not similar to one another. However, what we can do is set up two different trig ratios here, because if I look from this viewpoint here, I have the opposite, and I'm going to call this side here, this adjacent side, let's call that Y. Now I know that from this viewpoint here, this 42 degree viewpoint, I also have my opposite side as well as this adjacent side here, which I'll call Y plus 100. So really I'm setting up two different trig ratios, but I end up with the same opposite side here. So I have the tangent of 50 degrees is equal to the opposite X over Y. And I also know that the tangent of 42 degrees is equal to the opposite X over, this time, Y plus 100. So what I want to do here is try to set these values equal to each other. Okay, I can solve for X in both of these cases. So I end up with X equaling Y times the tangent of 50. And over here I have X equaling Y plus 100 times the tangent of 42. Now I can set these expressions here equal to one another. So I have Y times the tangent of 50 equaling, and that's degrees, so I shouldn't leave those off, equaling Y plus 100 times the tangent of 42. And then I'm going to solve for Y. So in this case, I do need to make sure that I plug Y back in so that I can solve then for X. So I'd have to come back here, either to this equation here or into this equation here, and then substitute Y back in. But first, we definitely need to solve for Y first. Now this algebraically is kind of tough, I think, for some students to see. We end up distributing here, so we have Y times the tangent of 42 minus 100, or I'm sorry, plus 100 times the tangent of 42. And then that equals Y times the tangent of 50 degrees. Alright, I want to collect my Y's to one side. Now I know that this looks strange, but this is just a number, and so is this. So when I try to collect like terms here, I can move those to the same side. So I have Y times the tangent of 50 degrees minus Y times the tangent of 42 degrees equals 100 times the tangent of 42 degrees. Now I want to, let me erase here, I want to factor out that Y so that I have the tangent of 50 degrees minus the tangent of 42 degrees, and then from here I can just divide out this entire expression here. So I have on the other hand side 100 times the tangent of 42, and I will divide out the tangent of 50 minus the tangent of 42. And now I have an expression for Y. So we have Y equals 100 times the tangent of 42 degrees divided by the tangent of 50 degrees minus the tangent of 42 degrees. All right, now we are going to, like I said, we're going to have to replace this now into either one of those original equations. I bet it's probably easier to do it right here. But we have to solve for x. Oops, not even in that one. Here, we already have solved for x. We just take y now and multiply that by the tangent of 50. So I'm going to take this entire expression here, multiply that by the tangent of 50 degrees in order to end up with the height of this building. Okay? So that's basically a little bit trickier, obviously, than the problems that we've seen so far with our application problems, but still doable. You're just going to set up maybe two different trig functions and try to set them equal to each other, somehow relating the two together. Okay, problem 2 here is definitely more abstract. It asks you to express a, b, c, and d in terms of just theta. Now right away I recognize that a here is this vertical segment. Okay, we are dealing with a unit circle because we can see here we have a radius here of 1. But a, this segment length, is just going to be the y value here, which in terms of theta is the sine of theta, right? Y is defined as the sine of theta. So we know a is equal to the sine of theta. That means that d here is equal to the cosine of theta. Now we also want to be able to express b and c here. Now just because this circle, or this segment appears outside of the circle, does not mean your ratios change at all. In fact, these are actually similar right triangles, right? Well, that trig ratio holds true still. We have our opposite side, and any side here we can pick. I'm going to use the adjacent side though, because instead of looking at this and thinking that you don't have the adjacent side, remember this is just a unit circle, right? So this side here, this segment's length is 1. So we actually know this value, so we can say that b, that segment here, is the tangent of theta. Okay, so let me explain why it's the tangent of theta. From theta's viewpoint, you have your opposite b over 1. So we have tangent of theta is equal to b over my adjacent 1. So obviously here we have b equals the tangent of theta. Now if I want to solve for c in terms of theta here, from theta's viewpoint I have the hypotenuse and I have another known value here. You could consider b a known value because now you know that it's the tangent of theta, but you also have the d value here, right, which is, I'm sorry, not d, the whole segment here, which is 1. So we can set this up two different ways. So from theta's viewpoint, I have the opposite, and I also have the hypotenuse. So I can say the sine of theta is equal to b, which is really the tangent of theta, over c. Now if I want to solve for c, I have c is equal to the tangent of theta over the sine of theta. Now in this case, I would want to simplify here. So remember, sine of theta over tangent theta is now being divided by the sine of theta. Well, those sine thetas will cancel. Whoops, I didn't mean to write tangent, I meant to write cosine of theta, sorry. So the sine of theta over cosine theta, that represents the tangent of theta, and then I'm dividing that by the sine of theta, and like I said, those will cancel, so I have 1 over the cosine of theta, which is really secant theta. So I end up with c equals the secant of theta. Now alternatively, if we had chosen to use this segment here, this 1, now I have the adjacent side and I have the hypotenuse, so I could use cosine. I could say the cosine of theta is equal to my adjacent 1 over c, and if I solve for c here, I have 1 over the cosine of theta, which is, of course, the secant of theta. So in either case, by defining these correctly, you'll arrive at the same definitions. So we have a equals the sine of theta, d is the cosine of theta, b is the tangent of theta, and c is the secant of theta. Okay, last up we have problem 3, which says in the figure below, segment AB is 24 inches long. We're supposed to express x as a function of theta. Now if you feel comfortable, you're more than welcome to just pause the video and try this problem on your own. There's lots of different ways that you can problem solve through this problem. I'm just going to show you how I approach the problem and kind of what my thought process was. Okay, so immediately when I try to express x as a function of theta, I need to somehow get theta within this triangle here. And I realize that this measure, theta, is actually congruent to this measure here because these are corresponding angles. So here I have a similar triangle. That measure must be theta as well. And now I can at least express x in terms of theta if I just label another side here. So I'm going to label another side let's call that side B here. And I also know that AB, that whole length, is 24 inches long. Now I can express that missing portion then, if this portion here is B, I can call that 24 minus B, or I could call that, you know, a different variable. I'm actually going to call it a completely different variable here. And then I have like a general equation that I know that A plus B, if I added those together, that would have to equal 24. Now if I want to express you know, x in terms of theta here, I can say that the cosine of theta is equal to x over b. Now if I solve for b here, I have that b is equal to x over the cosine of theta. So now I can make that substitution in here. Okay, and I'm going to do a very similar process now for trying to define a, because if I can get a out of there, now I'll have just x in terms of, you know, with theta. Okay, so I'm just trying to decrease the amount of variables that I'm using so that I just end up with thetas and x's here. All right, now in this particular triangle, I have the opposite side and I have the hypotenuse. So this is the sine of theta equaling 10 over a. So a is equal to 10 over the sine of theta. So again, I can make that substitution in here. Okay, so now I have a completely new equation. I have 10 over the sine of theta, which is a, plus x over the cosine of theta must equal 24. So I'm going to solve for x now. Okay, that was the b that I just substituted in there. I'm going to solve for x because now I'll have x in terms of just theta. So I would subtract the 10 over the sine of theta, and then I would multiply by the cosine of theta here, so I have x equals 24 times the cosine of theta minus 10 times the cosine of theta over the sine of theta, which is really just the cotangent of theta. So I have x equals 24 times the cosine of theta minus 10 times the cotangent of theta. So this is how I write and express x as a function of theta. So notice that in my final answer here, I have x completely isolated, and it is also in terms of just theta. I don't see any other variables here, because you definitely want to make sure that you only have it written as a function of just one variable, theta. Okay, that's the end of the lesson. I'll see you guys in class tomorrow.